phase induction motor with single stator winding, that is with only the main winding without any auxiliary means applied to that, inherently has no starting torque. Repeat once again. Single phase induction motor with only main winding without any provision of auxiliary means to start the motor are inherently having no starting torque. In other words, single phase induction motor having only the main winding in the stator without any auxiliary means provided is not self-starting. However, if the rotor is given an initial rotation by auxiliary means in either any of the direction, negative or positive, whatever you like, the torque due to the rotating field acting in the direction of initial rotation will be more than the torque due to the other rotating field. That means we are basically assisting one of the field, maybe the forward rotating field or the negative rotating field. So obviously, since we are assisting the rotation for a particular field, obviously the initially the torque for that particular rotating field, be it forward or negative, will be more than the other field. So obviously the motor will develop a net positive torque in the same direction as the initial rotation. Therefore, in that case, the motor will therefore keep running in the direction of the initial rotation. Now let us move to the next topic, rotor slip. So you understand that since we are talking about the synchronous speed, so we have to consider the rotor slip, just that we have done in case of three-phase induction motor. But there is a slight difference in the single-phase induction motor, since there is forward rotating field and negative rotating field or backward rotating field. So there is a slight variation compared to the three-phase induction motor. So if a rotor is rotated by auxiliary means, we consider that the rotor is now rotated by auxiliary means. So it will develop torque and continue to run in the same direction as one of the fields. So by definition, the direction in which rotor is started initially will be called as forward field. Okay. Now let us consider ns to be the synchronous speed and n to be the rotor speed. So by definition, slip of rotor with respect to the forward rotating field will be, since we have considered forward slip, let us consider forward slip to be simple s equal to ns minus n by ns equal to 1 minus n by ns. Let us consider it to be equation number 3. Now since the backward rotating flux rotates in the opposite field stator, the sign of n must be changed. Yes or no? Because we consider that there is a opposite rotation of the motor when there is a opposite flux. So n must be taken a negative sign compared to this one, right? So change in the equation number 3. This will be equation number 3. We have to modify this equation for the backward slip to obtain the backward slip. So thus the slip of rotor with respect to the backward rotating field is SB equal to ns minus, there is a double minus sign, so ns minus n by ns equal to 1 plus n by ns. So understand that there is a negative sign, there is a positive sign. So there is the difference. Okay. So by negative sign we get the forward field, by positive we get the backward field. This is quite similar to that of the forward field and the backward field that we have considered. You see here there is a negative sign, we talk it as a forward field, and for the positive sign we have considered it to be the backward field. There is a similarity between the slip equation with the flux equation and the slip equation. So if let the backward slip to be equation number 4. Now adding equation 3 and 4 we get s plus sb equal to 1 minus n by ns plus 1 plus n by ns. So this will cancel out. So we get here only 2, correct? So in other words we say backward slip is equal to 2 minus s. So make it equation number 5. Thus the rotor slips with respect to the two rotating fields are different and are given by equation 3 and 5 that we have discussed. In order to make clear the influence of the two rotating fluxes on the rotor, it will be assumed that n is less than ns. In case of three-phase induction motor, also we have considered that rotor speed cannot exceed the synchronous speed. If the rotor speed is exceeding the synchronous speed, we get the induction generator. So since we are considering only the motor case, so we consider that rotor speed is always less than the synchronous speed. So equation 3 corresponds to the motor operation and equation 5 denotes the braking region. So this equation denotes the braking region. Okay. Obviously, it should be a braking region since it is opposing the backward field is opposing the forward field. So that's why this name is logical braking region. Okay, the two torque have an opposite influence on the rotor. Now let us consider the rotor equivalent circuits. The rotor equivalent circuits for forward and backward rotating fluxes are shown in figure number 3. At standstill, the impedances are equal. You remember that in case of 3-phase induction motor, we have derived the equivalent circuit considering that all the 3 phases has 1 phase. So, there we have got this R2 by S, correct? And you understand that here we have got the derivation to be 2 minus S. So, we have replaced the backward field to be 2 minus S. All the other things will remain same. And you note that for the forward field, the current is 1 I2F, and in case of backward field, obviously it should be I2B, and X2 will remain same. X2 will remain same, but what is changing is the resistance part, where instead of R2 by S, where we have considered S to be forward field, so backward field is this should be replaced by SB, that is 2 minus S with respect, that is both the equations are having same term, that is S. So it is SF. Okay. So as standstill, the impedances are equal, as I already mentioned. Therefore, why it is equal? Why impedance should be equal as standstill? Because what is sleep? Sleep is equal to N minus Ns by. Let us consider the Ns minus N above whatever 1 minus N by Ns, right? As per equation number 3. Let us go to that part. Yes, here. So. Here. So your this speed is 0. So 0 means it is 0. So this becomes 1. Slip becomes 1. Forward slip becomes 1 at standstill. At standstill. Wait. And here also what happens? H becomes what? 1. So 2 minus 1 is again 1. So at standstill, yes, at standstill what happens? SF is equal to SB is equal to 1. So here it becomes R2, correct? And here 2 minus 1 is again 1. So this also becomes R2. So at standstill, the total impedance, obviously X2 R2, here is X2 R2. So total impedance remains are equal, correct? So impedances are equal, and therefore the current 2F, I2F and I2B are equal. Obviously it should be, because if impedance is same, voltage supply EF, EB both are same, because we are supplying only the single phase supply and we are considering only the main winding is there. So obviously the EMF induced is same. So in that case, the currents will produce MMF which oppose the stator MMF equally. Therefore, rotating forward and backward fluxes in the air gap are equal in magnitude. So no torque is developed at standstill. No torque is developed at standstill. Because the impedance becomes equal. So the flux produced by the two field, that is the forward and backward field, becomes equal and opposite. So the net torque will be 0. So there will be no torque and motor will not rotate. However, the rotor rotates. However, when the rotor rotates, why rotor rotates? Because by auxiliary means we are trying to rotate. Okay, by auxiliary means say we started to rotate. So as soon as you started to rotate the rotor, right? Rotor is rotating means we are having some value of n, that is the rotor speed. So slip will change correspondingly, correct? So impedance of the rotor circuits are unequal and rotor current I2B is greater than the rotor current I2F. Why it is happening? Let us consider. We know that if you consider that this is your speed n and this is speed, so value of slip will be having a dropping characteristic as speed will increase. Correct? So slip is no longer 1. So if you are having here, say at this position, say it is 0.8. Correct? 0.8. So you put here 0.8. So what will happen? And you put here 2 minus 0.8. So what happens? Is equal to how much? 1.2. Correct? So here in this case, impedance ZB, and here it is impedance ZA, correct, is higher and this impedance is lower. So current is V by Z. So in this case the current will be higher, correct, and in this case the current will be lower, correct. So our rotor circuits, impedance of rotor circuits are unequal. Unequal means obviously we say that ZA is greater than ZB and rotor current 2B is greater than the rotor current I2F. Their MMF is opposed. The stator MMF will result in reduction of the backward rotating flux. Yes or no? Their MMS. Which MMF will be higher? I2B. Which opposes the stator MMF will result in the reduction of the backward rotating flux. Consequently, as the speed increases, the forward flux increases while the backward flux decreases. You understand that you are having a drooping characteristic. So as the speed n increases, so reverse thing happens. The forward flux will increase and the backward flux will decrease. However, the resultant flux remains essentially constant. This resultant flux induces voltage in the stator winding. Both flux waves induce voltages in the rotor and produces torque in the rotor. This both flux wave induce voltages. So we have to always consider the flux and the torque produced by the individual fluxes forward and backward field, and we have to take the resultant of these two to get the actual flux which is responsible for keeping the rotor rotating. We will go to a graph. We will try to plot the graph because since the slip will change with respect to the increase in n, that is the rotor speed. So obviously the flux will first decrease for forward field, then it will increase further. So we need to plot it. These two torques are in opposite direction. The net induced torque in motor is equal to difference between these two torques. You can see in figure 4. We have plotted whatever we have discussed. The plot is given over here. Initially, you understand that at standstill, we already discussed at standstill, since these two are equal, you can see here, so net torque is 0. You see here, now we rotate the rotor by some auxiliary means. So what happens is that we will develop some forward backward rotating magnetic field. So it will produce some torque. You can see here the torque forward field, torque for forward field. And here we have the torque for the backward MMF. Okay, so you see here that this forward field is more. So when forward field is more, so the backward field is less. Correct. So if forward field is keep on increasing, on the other hand, the backward field is keep on decreasing. However, the reverse thing happens on the left hand side. You see here the forward field keep on decreasing, so the backward field keep on forward field decreasing. So backward field is increasing. Just the opposite thing is happening. Okay. So we get a resultant torque. Okay. That means in the right hand side, if you consider the right hand side, you can see that both the MMF are not equal. So torque production will be unequal. So that obviously the difference we get some torque. Similarly, in the negative on the left hand side also, there is a difference in unequal torque is there for the forward and backward field. So we get a resultant torque, which keeps the rotor rotating. But once again I mentioned that at standstill there is no torque. Torque is 0. Now, if the voltage drops across the winding resistance and leakage reactance are neglected, because we have included the voltage drops. Now let us neglect the induced voltage. If the voltage drop across the winding resistance are neglected, the induced voltage is almost equal to the applied voltage. So we have considered initially that the EMF induced are same, correct? So here let us consider that there is some EMF, induced EMF, EF is not equal to the here in case of EF and it is EB. So let us consider that there is some amount of loss because of the air gap and the induced voltage, whatever is induced in the rotor from the stator winding, there is some amount of leakage drop is there, okay, because of the air gap. So obviously EB should be less than that of induced input voltage. So in that case, there will be a slight change in the figure number 4 of this torque characteristic. You can see here that little bit bulge will be here. Here also there little bit bulge will be here. You can see the figure number 5 over here. So you can see that there is a difference in this part only. Okay, but the peak point and this peak point is not changing. If you compare these two figures, let us consider these two figures side by side if possible. Right? Yes or no? So you can see here this point around here, but it is not. It is almost same here also. Okay. So most of actually the working principle or whatever phenomena is happening is same. What we are, because we are neglecting or not neglecting or including, that doesn't matter. But there is a small change in the torque characteristic with respect to the synchronous speed. Okay, that's all for today. Thank you.